Sounds good. Okay, so our next speaker is virtual, and that is Grace Telford, who's a postdoc at Rutgers. So Grace is going to tell us about the ionizing spectrum of an extremely metal poor O star powering an H2 region. Go ahead and share screen when you're ready, Grace.
All right. And can you hear me and see my slides?
Looks good.
Great, thank you. Okay, thank you for that introduction. And hello, everyone. I'm presenting from New Jersey today. I wish I were in Pasadena with you all, but thank you to the organizers for making hybrid an option. So I'm going to tell you about some recent KCWI observations of an H2 region in a nearby dwarf galaxy, and what that can tell us about extremely metal poor O star models. Okay, so given the recent launch of JWST, there's obviously a lot of excitement in the extragalactic community right now about using new observations of these high redshift galaxies to determine which galaxies are dominating cosmic reionization. For the low mass galaxies in the early universe, feedback from metal poor O and B stars is not only regulating star formation in these galaxies, but it can also carve channels in the dense ISM through which ionizing photons produced by those stars can escape into the IGM. And to constrain the contribution of those galaxies to the ionizing photon budget requires a few model ingredients. So we want to calculate this ionizing emissivity. And in recent years, observations have actually given us pretty good constraints on the UV luminosity function as a function of redshift, and on the fraction of ionizing photons that can escape typical galaxies. And of course, we'll be getting better constraints on these in the coming years from JWST. But this third ingredient in the calculation, the ionizing photon production efficiency, this comes from stellar models. And in the very low metallicity regime that is relevant for low mass galaxies in the early universe, these models are purely theoretical because we have very few observational constraints from observations of individual O and B stars at such low metallicities. Below the 20% solar metallicity of the Small Magellanic Cloud, star-forming galaxies that are more metal poor than that are found at much larger distances from us. And so observations of individual stars become very expensive, and important stellar properties that impact ionizing photon production remain highly uncertain. So for the rest of my talk, I'm going to address this problem using observations of the galaxy Leo P, which is 3% solar metallicity and close enough to us that observations are feasible. And this is a special galaxy because it has only one known O star that is powering the only H2 region in the galaxy. So it's really a unique opportunity to test models of ionizing photon production at the very low metallicities typical of reionization era dwarf galaxies. So the rest of my talk will be focused on these three questions. First, what are the typical properties of these very metal poor O stars? And how many ionizing photons can they actually produce? And what are the shapes of their ionizing spectra? I'm going to start by giving some context for the current state of knowledge, how these very low metallicity stars behave. So I said I would focus on the one star in Leo P for this talk, but it's actually part of a sample of 3 very metal poor O stars, of which our team has recently gotten far ultraviolet spectroscopy from HST and COS. And we've focused on dwarf stars in particular because they are still on the main sequence. So we're getting a new look at the properties of these stars during their longest lived evolutionary phase and when they're the hottest in their lifetimes. So the FUV spectra give us information about two key stellar properties that impact their ionizing fluxes: their stellar mass loss rates and their rotation rates. So first, I'm showing the three FUV spectra ordered from lowest to highest metallicity on the slide. And I've zoomed in on two features that are sensitive to stellar winds. And it's easiest to see in the most metal-rich star at the bottom of the screen. So this broad blue shifted absorption is caused by the expanding stellar atmosphere with a dense wind. But when you look at the two stars that are below 10% solar metallicity, there's no evidence of a stellar wind in this nitrogen 5 line, and there's very weak carbon-4 absorption. And so these stars have to have very low mass loss rates. And this implies that they are going to be long-lived and potentially have harder ionizing spectra. Now, turning to rotation, I measured the projected rotation speeds, V sin I, from broadening in some photospheric features in the FUV spectra. And my measurements for the three stars are shown as these black vertical lines, with the two below 10% solar shown as solid lines. And the distributions are showing samples from the literature of similar late O-type stars in the small Magellanic Cloud, so at 20% solar metallicity. And from this plot, you can read off that the two very metal poor stars are both rotating faster than about 90% of similar stars in the slightly higher metallicity galaxy, SMC. And so it's unlikely that we would have found this if the very metal poor O stars had been drawn from the same V sin I distribution as we observe in the SMC. And so though the sample size is small, this is hinting that at very low metallicity, fast rotation may be quite common. And again, fast rotation would imply hotter surface temperatures at a given evolutionary phase and a longer stellar lifetime, which would boost the total ionizing photon production of these stars. So our FUV spectra have given us some insight into how these stars are actually behaving in this very metal poor regime, and hint that we may not understand their ionizing spectra as much as we would like. So this leads naturally into the next part of the talk. How many ionizing photons can these stars produce? And so this is where KCWI comes in. So we observed this field in Leo P, shown as the white rectangle on the left, with KCWI in early 2021 and earlier this year. And on the right, I'm showing a white light image constructed from one of these co-added data cubes. And the spherical bright H2 region really pops out here in yellow. And the other sources in this image are nearby cooler B-type stars. But I can construct a narrowband H beta image from this data cube, and then the nebular emission pops right out, and you can see the H2 region. So I can sum all of the spectra in these pixels to get 99% of the flux produced by the H2 region and get an integrated spectrum from these IFU observations. And this is the result. So you can see there are nice stellar absorption features, the broad Balmer absorption here. We have some helium-2 absorption as well, but the most prominent features in the spectrum are the nebular emission lines. And we have lines from a range of ions that require different ionization energies to produce. And so the relative strengths of these different lines is encoding not only the gas properties in the H2 region, but also the shape of the star's ionizing spectrum. So the first thing we can do with this data is calculate the photon production rate that's capable of ionizing hydrogen. So it's an analytical equation here. We need the H beta luminosity, and the IFU observations are key for this because we have an integrated measurement of the H beta flux and don't have to worry about slit losses. So we combine that with the well-known distance to Leo P to get our H beta luminosity. KCWI also observed the oxygen 3 lines that determine the temperature. And we measure these recombination rates at the correct temperature for Leo P. And finally, we have to assume an escape fraction. And I've already showed you images of the galaxy where the H2 region is pretty clearly spherical, almost like a nice Stromgren sphere. So it's not disrupted and not obviously leaking photons. And so it's reasonable to assume that the escape fraction is small. So we assume 0. And then everything else here is a constant. And so we can calculate this ionizing photon production rate of 3.9 times 10 to the 48 photons per second. So how does that compare to stellar model predictions? Well, from the analysis of the star's FUV spectrum, combined with optical and infrared photometry, we have a best fit model to the spectral energy distribution of the star that predicts its ionizing spectrum. And I can count up the ionizing photons in that model, and I find 4.2 times 10 to the 48 photons per second, which is remarkably close to what we measured from the KCWI observations. It's agreement within 10%, which is remarkably good considering that no one has ever been able to test stellar models like this at such low metallicity before. So finally, the last part of the talk, what about the shape of this ionizing spectrum? So here's the same model, just shown in a different way now. What we've just done is count up all the photons more energetic than 13.6 eV, but we have much more information than that. We have lines that probe the amount of photons available above all of these different ionization energies. And there's no straightforward analytical way to calculate those ionizing photon production rates, but we can use this ionizing spectrum as this ionizing source in a photoionization model. So plug this into Cloudy and predict what what emission line emissivities we should see and compare to our KCWI observations. So here I'm plotting ratios of the line intensities relative to H beta as a function of wavelength. The KCWI observations are represented in black and the Cloudy model prediction is in red. So the strong lines are well matched, but most of our line detections are down here. So if we zoom in, we can see that this model can approximately reproduce the strength of these metal lines spanning a range of ionization energies. And so again, this is really quite encouraging. It suggests that the shape of the ionizing spectrum is about right too. And it's I think it's quite a success for these theoretical models at such low metallicity. Okay, so this brings me to my conclusions, and I think I'm low on time, so I'm going to leave these up and just emphasize that it's the IFU capabilities of KCWI combined with the large photon collecting area of Keck that really allowed us to do this test. And it's the first time we've been able to validate stellar spectral models at such low metallicities that are relevant for modeling reionization era galaxies. So thank you for your attention, and I'm happy to take questions.
Thanks, Grace. This is really cool stuff. Let's see, there are no questions on Slack. Are there questions in the room?
John O'Mara. Do you have any other places you want to go other than Leo P?
Yes. So we have KCWI observations in the other 2 galaxies that host the stars I mentioned at the beginning of the talk. So Sextans A and WLM. And there are no other, lovely spherical H2 regions holding just one O star that would provide quite as clean a test as we have in Leo P, but certainly I intend to do similar analysis in those galaxies.
Oh, I bet I had this one. Do we know if this star could be a binary?
Was the question, is it a binary?
Do we know if this star is binary?
So it is possible. but nothing in any of my analysis requires a binary companion to explain our observations. And I actually think that the agreement between the single star model spectrum and the KCWI nebular emission, it argues that it's a single star, but I cannot say for certain.
We have time for one more fast one. Anyone?
What do you want KCRM to do with it?
Well, I'd certainly like to go back and look at this H2 region again and get coverage of redder lines so we can have density diagnostics, for example. We didn't cover the oxygen 2 doublet with these, so we could do a lot with more detailed measurements.
Okay, that's us out of time.
Great, thank you very much.